So during last week, this week, what have we been doing? We've looked at phase transitions in materials that were non-magnetic, the nickel-titanium shape memory effect and things. And then we got into the magnetic aspects of it. We looked at magnetic shape memory effects. And what we see is that the functionality is not limited to a magnetic shape memory effect, but there arises of many other functionalities like the magnetocaloric effect and so on in these systems. We have magnetostructural transitions, and at magnetostructural transitions we not only go from one structural state to another, but also from one magnetic state to another magnetic state. In many cases we can guess what the magnetic states are. The high temperature states are usually more trivial than what is happening at low temperatures, and especially in the case of Heusler's, I haven't told you anything about what the low temperature phase is until now, right? We had the antiperovskite. That was okay. It went from a ferromagnetic to an antiferromagnetic state, but we had no proof for that either. I mean, yes, it seems to be the case from the magnetization data alone. And then we looked at the some of these pnictide-like systems, the manganese antimony based systems, and they go from a ferrimagnetic state to an antiferromagnetic state. It appears to be so. So then we have the Heuslers. They go from a ferromagnetic austenite to something martensite. And just exactly what is that something? Yeah? And the magnetization tells us that there is something there. It drops very rapidly, but it doesn't give us any idea of what the interactions are. We know that they are non-ferromagnetic, but just exactly what they are, we don't know. So to go into more details and to understand this, and so that I have a chance to tell you what those states may be, we will be looking at the samples that we have studied using some neutron techniques. Okay. Now I will. There's a saying that also says that neutrons always tell the truth. Yeah, you can say whatever you want, but neutrons see things. Yeah, they have a magnetic moment, and they will diffract. They will give you information on the surrounding magnetism and on exactly what's going on with the structure. So neutron is therefore a very powerful tool. So you get information both on the structure and on the magnetization. So now I'll just review some very basic things on how we interpret the neutron data that we see. And I'll also try to introduce you to some methods which we use to understand the magnetism of these complex systems. So now if we have a simple ferromagnetic structure, you know, the neutron carries a magnetic moment. It sees the magnetic structure as well as the crystallographic structure. If we have a structure like this, it's just depicted, where we have a ferromagnetic alignment on a certain lattice, then what you will get is, when you do a diffraction, the intensity over the Q. I wrote this as Q. You can write it as angle if you want to. It doesn't make any difference. They're related with this relationship over the neutron wavelength, lambda, and the diffracting angle. We have a peak at a certain Q value. Now this peak consists of two additive parts. One is the diffraction associated with the structure. And then on top of that, in this hashed region here, we have an extra intensity that comes from the ferromagnetic alignment. If you run the same experiment above the Curie temperature, then you lose this peak all of a sudden, yeah? And then from the intensity sitting on top of this peak, you can measure as a function of temperature that you'll see what you see normally in the magnetization, yeah? So now, what would happen if we had an antiferromagnet? Now, an antiferromagnet, the moment you have an antiferromagnet, the structural part, the peak will be here. But now, the magnetic unit cell is no longer this unit cell as in the ferromagnetic case, but it is twice this magnetic cell. So to be able to define this antiferromagnetism, you have to extend this over two cells here. So the in one particular direction, the magnetic magnetic unit cell is doubled. And when the magnetic cell is doubled, the lattice parameter of the magnetic unit cell is doubled. And as you increase the lattice parameters, your peaks shift to smaller values. And what happens is that here you see the appearance of another peak, which is the purely magnetic in nature. It doesn't have anything to do with the, it's not the structure, but this peak comes out as a magnetic superstructure peak at half the value, in this case, of this Q0 over here, of the structural peak. So, this is a very simple case. If you had other structures which were perhaps canted or with the spin in the other direction and things, this peak would come up in other places. It would have maybe some satellites and things, so that looking at the structure of this peak and where the peaks are coming out, you can say something about the magnetic structure. Okay? So, this is basically why we use the neutrons. Now, to give an example of this, let's look at some real data. This is nothing but our antiperovskite, the manganese 3 gallium carbon, which we talked about here. And this was the magnetization data that I had showed you before. It has a transformation from one state to a ferromagnetic state. We call this state the antiferromagnetic state. And then this here was the Curie temperature. And this can be measured in small fields and high fields. And you'll see some shifts here. If you do the field dependence of this, I had showed you this before as well. So you get, you're sitting in some, that temperature which corresponds to the low temperature phase. So you're sitting at 150 Kelvin here. It's antiferromagnetic. You're applying a field. You're inducing a transition to the ferromagnetic state. And when you remove the field, it comes back with a certain amount of hysteresis that's involved with it. You can you can do neutron diffraction experiments on this. This is what we had done. And you can take patterns at varying temperatures. And then looking at the temperature dependence of whatever the diffraction patterns are and how they're changing. From there you can determine lattice parameters and things like that, of course. But you can also see what is coming up magnetically or not. So this pattern is taken at 150 Kelvin. And this was refined. So you have here the various contributions coming to this pattern. Mostly, it's the structure. That is just the standard, the Bragg positions, or when you're talking about neutrons, you call them nuclear Bragg positions or nuclear positions. And then you have the magnetic scattering, which you see here. So you see that this peak would not be there if you had measured this at high temperature. This is a purely magnetic peak which is coming out, this one here. And then you have peaks coming in from manganese oxide, which is an impurity in all these systems. You can't avoid it. When you make samples like this, you always have manganese oxide somewhere. So you have to look for it. And anything that you're refining with these things, you'll have your manganese oxide, mostly. Aluminum comes from the environment, from the cryostats and things like that that you're using in your setup. That's always there. And then we have some graphite. And the graphite, I think this particular peak, for example, that is there because when you're preparing manganese 3 gallium carbon and things like that, you have some extra carbon in there and things, and that comes out as graphite. So graphite is something else that you cannot avoid, but it just sits there. It doesn't hurt. So now you want to look at the temperature dependence of this of the diffraction to see how the structure is evolving, what is happening, and yeah, what peaks are coming out as far as the magnetism is concerned. So what we do is we sit at around 150 Kelvin, take this data as our reference data, and then we start, in this case, you can apply a magnetic field. I'm sorry, I said temperature dependence. I meant to say field dependence of the diffraction patterns. And as we apply the magnetic field, we'll be inducing our a phase transformation, and these should reappear in the neutron diffraction data. And the neutron diffraction data should give us details of what is going on during the transitions. Okay? So we have here data. This is at 150 Kelvin. And we are applying a magnetic field from 0 to 5 Tesla and then back down again to see how these peaks are evolving. We look at two particular peaks. One is a so-called half-half-half. That is at about somewhere less than 20 degrees. So it's this one over here. Okay? This is a magnetic peak. It tells us that this thing is antiferromagnetic. So this is now beyond doubt that it is an antiferromagnet. And then we look at the 332 peak, which sits at around 138 Kelvin. So it's this one over here. Now, manganese 3 gallium carbon has a high volume, low temperature state. That is in the antiferromagnetic state. Its volume is larger than in the ferromagnetic state, and it has a volume anomaly. This peak will give us information on how the magnetism is changing when we're applying a field. And this complex structure over here will give us information on how the volume is changing eventually. Now, in zero field at 150 Kelvin, this thing is antiferromagnetic, so we have a large intensity. Now, you see here that as we apply the field, as we go to higher and higher values, up to 4.8 Tesla, the intensity related to this peak goes down, and it vanishes at around 4.8 Tesla. As we induce the ferromagnetic phase. Now, when the ferromagnetic phase is stabilized at high fields, there's practically nothing left of the antiferromagnetism. So you can see here very distinctly how you are going from the antiferromagnetic state to the ferromagnetic state. This is one. Here, just not to complicate things, we've plotted the data in 0 Tesla and in 4.8 Tesla, just in the two extremes. Now, in 0 Tesla, the 332 peak, this is all one peak. It's 332. It's the 332 in the antiferromagnetic state, and it's the 332 in the ferromagnetic state. Now, the 332, the ferromagnetic state, has a small volume, and that means that the peak should be at a higher angle. So this is the peak in the ferromagnetic state, and this is the peak when the system is antiferromagnetic. It moves to smaller values, meaning that the thing has gotten larger. So what happens is that when you're sitting at 0 field, okay, this is your peak. It's sitting at this value. And then at an intermediate field of 3.5 Teslas, shown with these black dots here, you see that the intensity related to the volume in the antiferromagnetic phase is getting smaller. And what is happening? There's another peak that is appearing. It's not shifting. There's nothing shifting here. So one is going down, and another one is coming up. And when you go to 4.8 Tesla, this intensity has completely disappeared, and this has shifted all the way to the other side. So we see from this, it answers the question, is this volume change a continuous volume change, or does one volume appear as soon as the parts become ferromagnetic? And it turns out that the second case is here valid. There is no continuous shift. It just happens that a continuous shift would mean that as we increase the fields, this would gradually shift to the right. But we see that the volume associated with the antiferromagnetic state is causing a drop in the intensity as we're increasing the field, and another one is coming up. So we have small volume states and large volume states coexisting with one another in this transition. And when we have such coexistence, we have strains. Of course, we have small volume parts and large volume parts in the sample, and they have to match somehow crystallographically. And to match those will require the presence of strains. It gives rise to a strain state. So this also accounts for the hysteresis that we see here. Okay, because of these strains and things, we see the hysteresis in the field dependence of the magnetization. There are some parameters you can extract here and show this as some kind of a summary. You can determine the phase fractions of the antiferromagnetic and the ferromagnetic states. So in small field, this is all plotted as a function of field, these parameters. So you see that the phase fraction initially in the antiferromagnetic state is 100%, and as you go through the transition, the phase fraction goes to 0, and the phase fraction of the ferromagnetic state, of course, goes to 100%. If you look at the lattice parameters, the low temperature lattice parameters are large, the lattice parameter, the A parameter, and then there's a coexisting state here. This is not a drop, it's a coexisting state of the high volume and the low volume states here. And then this actually also disappears. And you can extract information like things on the magnetic moment. You see here that the magnetic moment in the antiferromagnetic state is larger than the magnetic moment in the ferromagnetic state. And you have here, again, mixed moment. states, depending on whether the mixture that you have, the part of the mixture that you have is antiferromagnetic or ferromagnetic. This B isoparameter is it's a parameter that is connected to the deviation of the position of the atom from its equilibrium position. Normally, this should be spherical because the atom can move in all directions equally well. But when you get into the strained state, suddenly you have some confinement. In certain directions it's more difficult to move. And then when you increase the field in the ferromagnetic state, the original value is recovered. It should be, so that the vibrations are spherically symmetric. This just gives you an indication that there is some strain involved at the transition point. Okay, are there any questions up to here? Because now I'm going to go into Heusler's.
I was just thinking that when we have this ferromagnetic and antiferromagnetic phase coexistence, so in that case, how that our domain structure will look? Because we will have ferromagnetic domains, and then how about antiferromagnetic? Can we say there are antiferromagnetic domains?
No, in the antiferromagnetism you don't talk about domains. You have we cannot say anything about the size of the. We're in the middle of a transition, okay. So we're sitting here, and we're going from the antiferromagnetic state to the ferromagnetic state. It is true. We have some it's a nucleation and growth process. So something nucleates here, and when it nucleates as a single domain, of course. Okay. Secondly, what you have is you're doing this in a magnetic field. You're applying a magnetic field, so most probably you're also influencing the nucleation at the same time. Okay, and you're growing something. As it grows, of course, it's going to build domains. Yeah, but at what stage of the transition these domains are built, and how the size of these change, we don't have any information on that. It's a good point. It would be interesting to look at, but we have never looked at that. We just say, okay, the ferromagnetic part starts growing, they grow. We never thought about the domains at this point, but that would be interesting. Yeah, at what field do you start building a domain structure? How would you probe that? I haven't given a thought to that. But you're right. I mean, at some point, domains have to be there. Yeah?
But there could also be that there are no domains because the ferromagnetic state is a soft ferromagnetic state. So at 5 Tesla, the hysteresis is already in the saturation region.
That is true. In the 5 Tesla state, there is no, you have a single domain. At intermediate fields, the field is still high enough to create a single domain. It's maybe only at very small fields that you may have to think about these domains, I suppose, yeah.
Because the saturation field is about 1.5 Tesla.
Yeah.
And you start seeing the ferromagnetic state around 3 Tesla.
I also think that because here the length scale is different. Because here we are talking about a unit scale. When we do with neutron diffraction, so we are actually probing at the unit cell level. And when we talk about domain, that means we are talking about n number of unit cells.
Yes.
So length scale will be quite different.
Yeah. That's true.
Yeah.
So, now we come to the same story where things are a little bit more complex. And that's the case where we have our various Heuslers, where they go from a ferromagnetic state to a funny state. Okay? And we have to find out what this funny state is. There have been some controversy in the literature that people have called this state over here a paramagnetic state based on Mössbauer experiments. Indeed, it is a disordered state, but thermodynamically it would not be possible to go from a ferromagnetic state to what we know as a paramagnetic state, because paramagnetic state we consider to be here. That's where all the spins fluctuate and things. There's no local ordering. There's no information from one spin to the other spin concerning their directions, concerning the alignment. And it's only when we cool it down they become ferromagnetic, because they are now informed of each other, the spins. They can communicate, and when they go to lower temperature, they're not going to lose the communication. They're still going to communicate, but the alignment is going to be perhaps different. That is another story. So, as you may recall, well, we can take nickel, manganese, indium, tin, antimony. I'll show you, depending on what experiment we had over here. We could be using any one of these because they more or less show similar data. Yeah, sitting at any one of these temperatures, applying a magnetic field causes these field-induced transformations, as we had seen earlier as well. Now you're acquainted with all of these. And what does this lead to? This leads to the magnetic superelasticity that I had introduced to you. The recoverable strains, actually these two data are more or less the same, show more or less the same thing. You apply a field, goes up, down, and you can reverse it, and you get things like this. So now, when we look at data like this, where the magnetization drops in small fields and in large fields, we want to know at this point, first of all, why they drop. Before going and doing any neutron diffraction experiment, of course, what you would do is you would study in detail the magnetization process at the temperatures where you think things are anomalous. So taking, for example, nickel, manganese, tin with this composition, we measure the field dependence of the magnetization at various temperatures. So we have 330 Kelvin, 300 Kelvin, and then 330 Kelvin, 306 Kelvin coming down, and then we have 300 Kelvin, and then 275, which corresponds practically to the minimum over here, and at 150 Kelvin, which is in this state over here. And as you can see, this is a mess. There seems to be no consistency until you take a good look at it and try to interpret it. I mean, it goes wild. So at 330 Kelvin, you're sitting in the paramagnetic state. It's close to the ferromagnetic state. It's almost ferromagnetic, but it doesn't get ferromagnetic. And your field dependence of the magnetization shows a curve that looks more like this. It's not straight, it's not linear, which you would expect more from from a paramagnet in this field range, but it's very close to the Curie temperature, so you have some para process going over there on, so that the paramagnet is indeed tending to align ferromagnetically at this temperature. When you go to 300 Kelvin, 300 Kelvin is exactly a temperature. It seems that that everything seems to be more or less ferromagnetic. So in contrast to the 330 Kelvin data, there's actually a very strong increase in the beginning. And then there is a slower increase, a slower steady increase, meaning that we have here not only ferromagnetic interactions, but also some non-ferromagnetic interactions that are causing this so-called high field susceptibility. That is, the high field susceptibility is a slope here. The higher the slope, the higher the high field susceptibility. And that tells us that we have non-ferromagnetic components of some sort in there that gives rise to this. So that's at 300 Kelvin. I forgot about 306 Kelvin, of course. 306 Kelvin is a temperature where it seems to be more or less, yeah, again, it's similar. There's this steep rise, and then there's this gradual bending. At 300 Kelvin, the steep rise is faster. So it seems that the ferromagnetic parts are saturating, but there's something left over, could be. Then we go to the next lower temperature, which is 275. And you see here, everything is dropped. So it looks like the 330 Kelvin curve, yeah? As far as the curvature is concerned, it starts from somewhere around 0, and then it curves up. So the people who said that it was paramagnetic, we're not actually too bad. I mean, it's a good assumption in this sense. It's just that it's not a paramagnet in the sense we know. It's not something that is fluctuating out. So if we then go to, so this area, since it looks like this, and it's below a ferromagnetic ordering temperature, it's suspicious. We have to look at that in more detail. And then when we go to lower temperature, which one is that? 150 Kelvin, suddenly the ferromagnetism is back again. Okay? It's not pure ferromagnetism. Again, there's this para process over here, so that it's a mixture of phases. You know, as I told you, this sharp rise is typical of ferromagnetic ordering when you apply a small field. And this broad variation with temperature when measured in a small field is not an expected case of a pure ferromagnet. So although this thing seems to go into saturation, there are mixtures in here of some other things that prevent this from being a sharp transition. So the questions we ask is, first, why does this drop? And secondly, why is this ferromagnetic transition smeared over the temperature? Those are two things we'd like to look at and see. Now, neutrons have a spin, so they can detect the magnetic structure, okay? Now, it would be very convenient if your neutrons had spins looking all in the same direction. Then you could really collect information, yeah, if you give them a well-defined direction. In this case, this is what we'd call as polarized neutrons. We can polarize them and then send them through our sample. So polarization is a process where your neutrons, which are unpolarized, they go through a polarization filter of some kind. Just like in light polarization, and you have these polarizers. Polarization is not the flipping of a spin and polarizing everything in one direction. Otherwise it would have been wonderful. We could use the full intensity. Polarization is a selection process by your filter. So your filter selects out a certain polarization direction, and the rest is thrown away, unfortunately. It's a very expensive process. Yeah, it's a waste, but it is like that. So here there is a little animation showing this. So we have neutrons coming in from the source. We have a polarizer, and we do indeed have a flipper where we can change the direction of the neutron if we want to. We have a sample or a no sample, in this case no sample at the moment, and then we have an analyzer and a detector behind it. So you may remember when you have light polarizers, you can use two of them, you can turn them around, light will come in. If you turn them around properly, then light won't pass through. It's a similar case. Here you have a polarizer giving a polarization, selecting a certain polarization direction, and an analyzer which reads a certain polarization direction. And by convention, We say that, okay, let this analyzer read something when the incoming neutron has an upspin, and the detector will detect that. If the neutron has a downspin, the detector will not detect that. So, the neutrons come in, they get polarized, and if the flipper is off, it goes to the analyzer and it reads something. Okay? Good. So, in the other case, if you turn your flipper on, then when the neutron goes through, it's going to be flipped, and it's going to go into the detector, and it's not going to see anything. So if you put a sample in there, your sample can do two things. It can allow the neutron to go through without changing its polarization direction, or it can flip it. It can do two things. If you have a paramagnet, your neutron will go through. If you have an antiferromagnet, your neutron will also go through without changing the polarization direction. If you have a ferromagnet, then it will depolarize in any one direction. The only thing that depolarizes a neutron are the domains, where the magnetization direction changes abruptly. So at this abrupt change of the magnetization, the neutron acquires an impulse which causes it to precess in some other direction. So it's not detected by the detector. So depending on if your sample has ferromagnetism in it, then it's going to depolarize. If it's fully ferromagnetic, it's going to fully depolarize. If it's partially ferromagnetic, it's going to depolarize to a certain extent. And you can do the so-called neutron depolarization experiment. You can change the temperature of your sample. If you're in the paramagnetic state, the neutrons will not depolarize, and you will find a high degree of polarization. And as you go through the Curie temperature, the neutrons will start to depolarize, and when you're in the fully ferromagnetic state, they will be fully depolarized. And to quantify this polarization, we define something called a flipping ratio. It's basically the ratio of upspins to downspins, and what is detected by the detector. If your flipping ratio is high, that means your beam is not depolarized. If it's low, then it becomes depolarized. So this is one thing to keep in mind, which we'll be dealing with in the experiments. The flipping ratio is a very easily measured quantity, which becomes a very useful, and especially to understand, first of all, whether your sample is depolarizing or not depolarizing. I want to go into just a little bit of detail concerning how the neutrons behave in the presence of a magnetic sample. Now, as you know, magnetism arises from two things. One is from the nuclear magnetism. That is, if you have an odd number of nucleons, protons and neutrons, then you have an extra spin. So the nucleus has a spin. It's not an ordered spin under normal conditions, but the nucleus has a spin. So the neutrons will also scatter from the nucleus. Yeah? Now, in addition to the nuclear spin, if you have your magnetic structure from the electrons, your electronic spin, it will also scatter from that. And the question is, how do you distinguish these two? And it's very interesting that that neutrons will distinguish the two. Considering nuclear spin scattering, let's consider this diagram first. This P is the polarization direction. So your neutrons come in, let's say, from the left, for simplicity, with a polarization in this direction. And then you have a magnetization vector with components along the x, y, and z directions. And then you have your scattering vector, the k. There are several conditions. I just want to show you them over here. You don't have to keep these in mind. If you're going to do this in your life, then you know what's going on if somebody tells you something about nuclear scattering and magnetic scattering. In the case of nuclear scattering, when any one of your spin components, mu x, y, and z, is perpendicular to the polarization, then you get this spin flip scattering. So let's say you're coming in this direction, the polarization is in this direction, and then k is in this direction. So mu y and mu x are perpendicular to the polarization. So these two components will cause a spin flip scattering. If the spin components are parallel to P, this one, mu z is parallel to P, so that just goes along, and that is non-spin flip scattering. Spin flip scattering only comes from magnetism when it has to come. Coherent scattering, that is scattering from the structure, is always non-spin flip. That we can put aside for the moment. Now, the magnetic scattering is a little bit different than this. In the case of magnetic scattering, you have your polarization, a condition where you have your polarization perpendicular to K, and a condition where your polarization is parallel to K. A further condition is that your polarization can be perpendicular to any one of these magnetization components, and it can be parallel to it. And because of these different conditions that you have over here, you can manipulate these mathematically to distinguish between the nuclear scattering and the magnetic scattering. This is something that I'm just telling you. It's nothing that you have to go through, at least at this stage. This is only to be able to follow what we are seeing in the data. But it's good to know these details so that you know there's something different about nuclear scattering and magnetic scattering. I mean, if you look at any one of these examples, you have the condition where your P is perpendicular to K and P is perpendicular to M. So in this case, mu x and mu y will give you spin flip scattering, and mu z will give you non-spin flip scattering. Now you can rotate the polarization so that it is along K, and if it's along K, then all these give you only spin flip scattering. Okay, so much for spin flip and non-spin flip. You have spin flip and non-spin flip, and you have flipping ratio. So what do we do with this? Just before going any further, I'll just show you this, what it looks like in a real spectrometer, okay, where we do these kinds of analysis. And then after the break, we'll continue with the rest. This is a sketch of a spectrometer at the ILL, it's the D7, where you can do all sorts of analysis. So you have your beam coming in from the reactor. You have a monochromatic beam of neutrons. You have your polarizer here. So as of here, you have polarized neutrons, and then you have your flipper. This can be flipped on or flipped off. You have your sample, and then it's scattered into a detector. So you have your multi-detectors to save on time, and so that neutrons are not wasted in this geometry. And then you have your analyzers here, and they detect your spin up If it's spin down, they get absorbed, they don't go into the detector. And so that's how you get, and moving around this detector bank covers your Q range or your theta range, and you get data. Okay? This is just to show you what a real spectrometer actually looks like. So we have, just to keep in mind, we have, we look at flipping ratios, and we look at the polarization analysis in terms of the various scattering conditions. We have nuclear scattering and magnetic scattering. Nuclear scattering, for our purposes, is always incoherent because the nucleus is not, the nuclear magnetism is not ordered, and the normal electron magnetism is coherent magnetic scattering. So we'll stop here. So much for neutron details. We'll go back to the magnetization data, and I'll show you how these magnetization data will be correlated to the neutron data and how we extract the information on this region, which we call funny at the moment. Bragg peaks. You know, Bragg peaks can be broad, Bragg peaks can be narrow. And in fact, Bragg peaks, in the case of magnetism, they can get so broad and broad and broad that eventually you have something diffuse, okay? Centered about a certain peak. So, if we have a very well sharp defined peak at half Q, that means we have a well-defined antiferromagnet in the structure, in the magnetic structure. If there are some deviations from the ideal magnetic structure, then these peaks can broaden. Yeah? And they can broaden so much that they will be kind of smeared out, showing a shoulder-like feature, but the center position of that shoulder would still be that half Q, more or less. Okay? This is for an antiferromagnet. Now for a ferromagnet, and a polycrystalline sample, again you have these additional peak intensities on top of the Bragg positions. If you have very diffuse scattering, then these will appear as broad shoulders around this peak as well. But there's one additional thing that will provide you information that you have antiferromagnetic scattering, ferromagnetic scattering, is to look at Q equals 0. Now Q equals 0 is the main beam. Of course, you cannot look over there. But if you go to a spectrometer where you use a large wavelength, so your Q range is limited, if you go to very, very small angles, then you can see what is happening around Q equals 0. Q equals 0 is also a Bragg peak. Okay? So, the scattering close to Q equals 0 is what we refer to as forward scattering. And I'll show you here the various kinds of scatterings that we obtain and how we obtain information from our systems. So now we come to, we take two samples. We have a nickel manganese tin and a nickel manganese antimony sample. This, you're familiar already with the magnetization, and in nickel manganese antimony with this particular composition, the temperature dependence of the magnetization looks more or less something like this. This is the Curie temperature of the martensite phase. This is wrong. I see this for the first time. That should be TCM. I'll have to correct that. I've been showing this to people for many years. But okay. Anyhow, we're in the martensite phase. And how do we know that? If we, this is a scanning calorimetry measurement. And you see here that the martensite start temperature is about 440 Kelvin. So it's up here somewhere. So this is the This is TCM. And this is our superparamagnetic behavior, right? What we've been talking about, more or less. Okay, so now, the first thing that you do when you're doing you're working with these polarized neutron diffraction experiments is to look at the flipping ratio. First of all, before you do any kind of an analysis, you do the simple experiment of measuring the flipping ratio as a function of temperature and over the full temperature range. When you do that, you have this data. This here is shown for the nickel manganese tin sample. Now, what does the flipping ratio tell us? You're up here in the paramagnetic state. The flipping ratio is something like this. It's defined as 26. It's an arbitrary number because you're just counting neutrons, and the instrument itself has an intrinsic flipping ratio because the analyzers are not perfect, the polarizers are not perfect and everything, and the instrument itself has a certain flipping ratio, which is the maximum that you have. And since this value of 26 is the case when the sample is in the paramagnetic state, or if you have no sample over there at all, because all the neutrons go through without being depolarized. So you have a high value of the flipping ratio first, and then as you go down in temperature, when you approach the ferromagnetic state, you have this tremendous drop. And this drop is due to the depolarization of the neutrons caused by the magnetic domains. So the magnetic domains are depolarizing the neutron in random directions. So the number of spin up and the number of spin down are equal. It's nearly 1. It's at a very low rate. Okay? So it's dropped. And then we come here. What has happened? This is where everything became interesting in these systems. You suddenly see that the flipping ratio starts recovering. It doesn't recover to its maximum value, but it is indeed recovering. Recovering means that you have lost many of the ferromagnetic domains that you had over there. There still are some, it's still depolarizing to a certain extent, but much of the ferromagnetic domains are gone. In fact, they go and go and go, and here there is a maximum corresponding almost to the minimum in the magnetization here. And as you may recall, when we did the field dependence of the magnetization measurements, this showed some kind of a paramagnetic response, but there was some ferromagnetism in there still as well because there was a certain curvature over there. So the beam here is not depolarized, fully depolarized, and the polarization recovers. And then what happens here? Then it starts dropping again. And it drops when it comes practically to this position over here. And then the beam is depolarized again. So this region over here, what we call the superparamagnetic, is perhaps not fully superparamagnetic, but there are magnetic domains built in there. If you don't have domains, you don't have depolarization. And in a superparamagnet, you don't have domains. But it could be that, of course, if the superparamagnetic parts are large enough and there is an abrupt change in the magnetization where the superparamagnetic parts are sitting in the antiferromagnetic matrix, then there could be a depolarization due to that. That we don't know exactly. But what we now know is that this drop is caused by the disappearance of ferromagnetism, first of all. I'm not saying the appearance of antiferromagnetism because we haven't done that yet. But ferromagnetism is disappearing, but not fully. There is still something there left over from the ferromagnetism. So then, the remaining ferromagnetism I said here, that could be also due to rest austenite because it's a martensitic transition. There could be something left in there, or could be something else as well. So now we go and look at what we obtained from our polarization analysis. Nickel, manganese, indium. We do an experiment at 500 Kelvin. 440 Kelvin was the martensitic transition temperature. So at 500 Kelvin, we're in the austenite state. At 320 Kelvin, we're in the martensite state. So if we look at only the structural part, not the magnetic part, only the structural part of the scattering, what we see is the peaks corresponding to the cubic structure. This is, of course, a very small angle, so that we observe only the first several peaks. And when we go into the martensite state, in nickel, manganese, antimony, this is all related. In this case, I think it's just the L10 state, the tetragonal state. Then if we look at this is the nuclear part of the scattering, the structure. Now we look at the magnetic part of the structure, of the scattering. These are separated by some mathematical manipulations. So what we see over here is we have data at 320 Kelvin, and we have, again, data at 500 Kelvin. At 500 Kelvin, we see something like this, which is growing as we tend to Q equals 0. So this range is about the range where we can sort of have to stop, because anything smaller than that comes into the main beam. This rise towards Q equals 0 tells us that we have, on some small scale, some ferromagnetic correlations. Okay? Q equals 0 would be a Bragg peak. And if there's anything peaking towards Q equals 0, from this data, we can say that we have ferromagnetic correlations. In many cases, not here, you would find that this peaking would begin to look like a Lorentzian, so that it would go like this, and then it would start going up here, and then you had to stop there. And if you look at the half-width of that, the half-width of that is proportional to your correlation length. From here, it is not easy to say what our correlation length is. It is so broad that it is in the order of the next nearest of the nearest neighbors. But to say something about that is not that easy from this data. But the only thing that we can say is that, yes, we have ferromagnetic correlations at high temperature, way above the Curie temperature. Okay? So when it comes down to the Curie temperature, there is a tendency for it to order ferromagnetically, but it does not. It undergoes a martensitic transition. So when you go below the martensitic transition to a temperature where you are, again, in the martensitic transition was here at 440, and we're doing our experiment here in the martensite state at around 330. Such experiments you cannot do in the magnetically ordered state, because the magnetism depolarizes it, and you cannot do polarization analysis, unfortunately. You get no information. So you have to remain either in an antiferromagnetic state or a paramagnetic state, or at most a correlated. So what happens here? Very interestingly, it appears that everything here looks more or less the same, but as soon as you are in the martensite state, you lose the ferromagnetic correlations. They're gone. You have a peaking around here at 1.5. If this were a peak, then you would say, I have an antiferromagnet. But this is not a peak. It's very broad. So it's some kind of antiferromagnetism that is either frustrated or it is on a very, very small scale. That gives you this very large ordering. So this tells you now, and then you can say now, that the magnetic ordering below the martensitic transition temperature is some kind of a complex antiferromagnetic short-range ordering. That's it. So we get the information over here on what this is. It's not a paramagnet. If it were a paramagnet, this would be straight. It's not straight. And you can do this for nickel manganese tin. This is a diffraction pattern taken over on a standard diffractometer. This is on the D7 where we have a smaller Q range. So these peaks over here, they correspond to this group somewhere around here. And here you are. Here we have several data on top of each other. They're colored, but can't see the colors here. We have at 504 and 405 Kelvin and 330 Kelvin. So there are three sets of data here, all on top of each other over here, which are at temperatures, taken at temperatures above the martensitic start temperature. So it's in the cubic state. And you see here very distinctly, you have this forward scattering. That tells you that the ferromagnetic correlations are there at high temperatures. And in addition to that, as here, when you have seen this drop, you can say that this thing here that you have in the back, which is also a magnetic scattering, is also related to some antiferromagnetic correlations. But here, the ferromagnetic correlations dominate. So at high temperatures, you have the ferromagnetic correlations and the antiferromagnetic correlations. And when you go to low temperatures, you're left with the antiferromagnetic correlations. These are off-stoichiometric systems. There's a lot of manganese in here, so you have lots of manganese nearest neighbors and manganese next nearest neighbors. That will become more evident in the talks that I give tomorrow and the day after tomorrow concerning INVAR. The nearer neighbor interactions in manganese are antiferromagnetic. The further apart manganese atoms, they act ferromagnetically, and here you see both. It's just that below the martensitic transition, it appears that the distances have exceeded a certain critical distance, and there's no ferromagnetism. Everything's gone down. And here also, you see that when you come down to 250 Kelvin, which corresponds to that minimum where you have some problems with neutron depolarization because of the ferromagnetic part in there, but the flipping ratio is still high enough to give you some information to allow you to make an analysis. And what you get is you get this broad shoulder, again, peaked around 1.5, somewhere around here. So we have short-range antiferromagnetic correlations. If you collect all the data together at 500 Kelvin in the austenite state of both samples and in the martensite state of both samples, you see here the clear distinctions. Now, this much information, yes, we have. Good. The rest remains on how the magnetic ordering really is present in here. And that requires some models and things. It's not that easy because we have modulated structures. Modulated structures may be complex, even if it's L10 or modulated, so that arranging an antiferromagnetic configuration in such structures would be not that trivial. And even if you had certain configurations, that may not be the only possible configuration. You can have an infinite number of configurations or a large number of configurations, so that you would call this something like a frustrated antiferromagnet with different ground states. And that would give rise to your broadening that we are seeing here. Okay? So now, another case is the case of nickel manganese indium. Nickel manganese indium, the indium atom is large. And we found that doing such experiments, sitting at these temperatures, is a little bit more difficult. We have our flipping ratio measurements. You see that the flipping ratio is high and then it drops and then it's down here somewhere. Now, what we see is in the black dots over here, if you can distinguish the black and the blue, they come down here. There's some feature occurring over here, but it's not that obvious. It could be that the correlations are not strongly antiferromagnet. What you can do is then you can put pressure, apply hydrostatic pressure to the system and try to bring the atoms a little bit together and to see if the interactions change. And indeed, if you do this experiment in a pressure cell, you see that if you go to about 15 kilobars, then you see that your the flipping ratio had increased, and it corresponds to a temperature where this peak is about the minimum around here. So indeed, putting pressure perhaps brings the atoms a little bit closer together so that you are on the favorable size of the critical volume so that your antiferromagnetism is seen there. Okay? All this is nice, and we can now try to understand what we have observed further in our antiperovskite systems. Okay? In our antiperovskite systems, we have very nice transitions from a ferromagnetic state to an antiferromagnetic state. We've shown that with the standard neutron diffraction experiments. If we run these polarization analysis experiments on our antiperovskite systems, then we can understand them even better. We actually want to understand the case of manganese, gallium carbon, nitrogen, where we had called this an enhanced paramagnetic state. We said that we don't have any ferromagnetic state over here. When we apply a magnetic field, we get a field-induced transformation from an antiferromagnetic state to some enhanced paramagnetic state. Since it's an enhanced paramagnetic state, it should have no domains. And if it has no domains, the beam should not depolarize. In the case of manganese-3 gallium carbon, we have the ferromagnetic transition and the transition from the ferromagnetic state to the antiferromagnetic state. When we look at the flipping ratio, when we run the flipping ratio experiments, we see that at high temperature, above 300 Kelvin, when everything is ferromagnetic, the flipping ratio is high, and then it drops to its minimum value when you cross the transition, when you develop the domains. And as you go back into the antiferromagnetic state, the flipping ratio comes exactly to the value which it had in the paramagnetic state, because you don't have any domains. Now let's look at this. When you look at the flipping ratio over here, nothing changes at this temperature. There's a tendency here to align ferromagnetically. There's a little bump over here, things like that, but I mean, it could be real, it's true. There could be some initial building of some domains over there perhaps, but it's not that significant. And if you go down further in the temperature, you see that the flipping ratio remains at its high value constant, so there's nothing depolarizing. Okay? So indeed, we said it was an enhanced paramagnetic state. That was a speculation. But now we have a proof for that. If we do these experiments as a function of temperature, when you're at very high temperature in the paramagnetic state, everything should be paramagnetic. But it appears that even at 500 Kelvin, it's not a pure ferromagnet. There is a tendency to peak towards Q equals 0, meaning that your states, your system is ferromagnetically correlated. You have very short-range ferromagnetic correlations. And if you go to 400 and 300, you can see that this peak develops and gets stronger, and well, below 300 Kelvin it depolarizes, so you cannot run the experiments anymore. But when you look at the nuclear part of this, you see that at 150 Kelvin, I'm sorry, it goes into the antiferromagnetic state, and at 150 Kelvin you're in the antiferromagnetic state. And what do you see? You see something peaking over here. So here you have your ferromagnetic correlations. There's something underneath here, and this peaks. And if you look below this peak, this is on another scale here, this scale and this scale. This scale is a large scale, this scale is a small scale. So if you expand the scale so that this peak is somewhere up there, you see that you have this diffuse scattering over here as well, meaning that you have, it's not a, okay, next to the antiferromagnetism you also have, say, some short-range correlations over there as well. When you go to low temperatures, you have your half peak, and then there's this other manganese oxide peak coming out. That's always there. You cannot avoid manganese oxide. It has a nail temperature of about 110 Kelvin or something, so that when you go to those temperatures, you have this. This left side is the structural part, and there, as you can see, nothing much changes, except for the fact that you have manganese over here and you have some graphite peaks as well as impurities. Now, in the case of manganese 3 gallium carbon, it is also, the data is also more or less the same. You have at high temperatures these strong ferromagnetic correlations. You see this bump coming up, which is eventually becoming a peak when the ordering occurs at the antiferromagnetic something transition. Okay? So in this case, you have a transition from an antiferromagnetic state to a to a enhanced paramagnetic state. There are no domains, and the fact that there are no domains and that perhaps there is not much volume change between the two systems tells us that this system is rather unstrained, so that when we apply a magnetic field and look at the magnetization, the curves retrace and so on. Increasing magnetization, on increasing field and decreasing field, the magnetization curves follow one another, and we lose hysteresis. Okay? So, this brings me to the end of this section, where we have investigated magnetic correlations with the help of neutron polarization analysis experiments. Are there any questions here? Okay, I'll be in the office in the afternoon, anyhow. So, the next thing that I want to talk about, not too much in detail, but as a last thing concerning the interactions that we have in these systems, is the phenomena called kinetic arrest. Okay, so we have all sorts of caloric effects, of course. We have shape memory. We have all these things. And it can be that these systems become inhomogeneous at times. And when they contain inhomogeneities, especially magnetic inhomogeneities, then we encounter some other kinds of effects. Kinetic arrest is the arrest of the transition, or arrest of the austenite state. So if you, by a magnetic field in our case, if you apply a magnetic field and cool through the transition, you find that the state, the high temperature state, is stabilized well below the transition as well, for some reason. Now, one of the first experiments was performed by a Japanese group on this phenomena on a nickel, cobalt, manganese, indium system. So what you do is you apply a magnetic field of 5 Tesla. Actually, they had made a mistake. They told me later that this was 8 Tesla, and this was 5 Kelvin. I asked them, so why do you do this at 8 Kelvin? They said, no, we do it at 5 Kelvin. And, okay, so it's 5, but you write in your paper that you're cooling in 5 Tesla. I said, no, we're cooling in 8 Tesla. So they had these 8s and 5s mixed up around here, but it's not that important anyhow. So you're sitting at room temperature in this system, and this system shows typically the temperature-dependent magnetization curve, which looks like any of the other ones, the nickel, manganese, indium, nickel, manganese, tin, except the transition temperatures are shifted a little bit. At 300 Kelvin, this is in the austenite state. This is L21, this is cubic. So you have the 220 peak. And then you cool this in a magnetic field all the way to 5 Kelvin, and 8 Tesla. And you see some peaks associated with the Martin state coming up, but this 220 is not lost. It's still there, okay, when you've cooled it in a very high field. So cooling it in a very high field maintains the austenite state all the way down to low temperatures. And when you decrease the magnetic field, you see that the system remains in that state. It's still there. So this is the direction of temperature change. So the temperature is cooling. It's cooled down to 5 Kelvin, and then we've decreased the field. And now they begin to increase the temperature. And what happens is that when they come to about 100 Kelvin in zero field, this is zero field warming after the 5 Tesla heating, so you remove the field here, this is all zero field, you see that this Martensite state starts reappearing again. And then at around 200 Kelvin, you have a pure Martensite state with some of your rest austenite, or the arrested austenite there. And then at 300 Kelvin, everything is back to its normal position. So the magnetic field has done something here. The magnetic field has arrested this state. Similar things you can observe in the neutron diffraction. Sorry. We have here, this is the at 5 Kelvin, and this is at 317 Kelvin. And if you apply magnetic fields, I showed you this before, that you can you go to a certain temperature, apply a magnetic field, you can go from the Martensite state to the austenite state. This is not kinetic arrest, it's just a field-induced transformation because we haven't cooled anything in field, but we can induce a reverse transformation. Now, if we take, again, a nickel manganese indium, and we are at 300 Kelvin, and we apply a field of 5 Tesla, we get a diffraction pattern that looks something like this. And then we cool it down in 5 Tesla to a temperature about 5 Kelvin. You see that these peaks have shifted because of the change in the lattice parameters, but the peaks associated with the cubic